Okay. Well, welcome everyone. I'll switch off the captions in a minute as well. Milos Rydval, if you don't know him, he's part of I guess, the original generation with Jesper and others around sort of a decade ago when they were using blue intensity for their PhDs. So now he's talking about kind of the next step of high resolution associated methods, I think that's I will pass it on to Milos.
Okay.
So everyone switch off the videos and microphones just in case, and I can monitor from this end. So over to you, Milos.
Cool. Thanks for the intro, Rob. So I'll jump right into it. So title today is Surface Intensity State of the Art. And this basically is some work that we've been doing as part of the Replicate project, which is ultimately focused on reconstructing temperatures, but this is kind of methodological addition or sort of aspect to what we've been working on over the past few years. So we all, I guess, are more or less aware that there's sometimes a quite substantial issue when it comes to color and sort of light reflectance property issues with blue intensity data. So any sort of discoloration can cause potential biases. We know this, from comparing blue intensity data with density data, for example. So that is obviously potentially an issue, especially when we're looking at longer term trends. Chemically, using chemical approaches and treatment, we can minimize that, but usually it's not a perfect solution. Then another sort of issue which we encounter with blue intensity, but this also affects density, is potential biases related to sort of the size of the rings. And specifically, this is essentially a limitation of the sensors that we're using to represent density, and when we're interested in maximum density, maximum liquid density, finding that point of highest density, and essentially the sensors are not precise enough, or the resolution isn't high enough to detect those peaks in density, particularly in very narrow and very small rings. So that's another limitation that's more related to resolution. And then sort of based on some work that Jesper published a few years ago, or actually recently, there's this idea that we could essentially represent density by looking at the anatomical structure and sort of just using a 2D anatomical sort of cell dimension representation of the cell wall area in relation to the total cell area. We can actually derive anatomical density, which basically got us thinking that this might be a useful way forward in terms of potentially just getting a representation of the surface of a sample at high resolution and using this principle to essentially establish anatomical density, or get measurements of anatomical density in this way. So this led us down the path of using microscopes, high resolution imaging techniques, and to essentially try to get this representation of the anatomical cell structure. So I'll just say a few words about the procedure or the process that we've been working on. So a lot of it is dependent on or relies on the surfacing of the samples. So we have oh my God, what's happening? Okay, so essentially the surfacing, we've sort of spent quite a lot of time developing a specific surfacing procedure to try to get the best surface possible, so that we can work with that and get the best possible representation of the anatomical structure. We also experimented a bit with staining of the samples, and just essentially just to get or sort of enhance and improve contrast, which can be helpful then when working with high resolution images. And then essentially using very fine chalk powder to fill in the lumina to, again, get that differentiation between the lumina and the cell wall. So here's here's the microscope that we're using. We have a motorized stage, which allows us to sort of get measurements in the X, Y, Z directions. Then we basically just kind of map the surface to try to avoid any big differences in the surface or in the height. Yeah, then it basically takes quite a while to get sort of a large mosaic of images to get a very high resolution representation of the surface. So that here's an example, just a little bit close up. So this takes a while, but the images are really quite nice. So here's a kind of a quick walkthrough. Basically, capture the images. So we have this large mosaic. There's we realized very early on that actually by using a polarization filter, we can really improve the contrast. So you know, rather than relying on staining of the samples, we could actually kind of get around this problem of limited contrast by using a polarization filter. Then we do some image processing and then actually invert the image and then work with it after that. So the bottom image is sort of our the image that we would measure. So just to kind of show that also in sometimes we experimented with staining as well. So here's an example of unpolarized version of that image and the polarization, the polarized light version, you can see a clear improvement in the contrast. So here we also have so the image actually then goes through a series of processing steps in order to get this sort of binary black-white representation of the sample surface to get that sort of cell structure. So here you can see that for one whole ring, and here's sort of the end result. So in this case, essentially, we don't have to worry about things like calibration, color biases at all, because we just take that out of the equation altogether. So here's a sort of a quick overview comparing sort of the standard blue intensity scans compared to high resolution, sort of full color image. So we go from about 2,400 dpi to 75,000 dpi. And then on the right, you see sort of in all the detail, the inverted binary version of the image. So just to kind of give you an idea of what that looks like and the level of detail and resolution that we can achieve here. So another neat thing is that when we have the binary image, actually what we can do is rather than sort of having to invert the data at a later stage, which we have to do in one way or another when working with images that are used for blue intensity, what we can actually do is before calculating this surface intensity parameter, we can actually just invert, or we just invert the image. So then we have sort of this inverted variant version, which means that we don't have to do any additional inverting or adjustments to get a direct relationship with ring width, density, climate, and so on. So that's quite handy. I'll give a few examples related, sort of based on some data or some samples that we processed as part of the Replicate project. So really just with from using Norway spruce samples from high elevation, you know, we really our focus in this project is to use ring width, large number of blue intensity sites. Now this new surface intensity parameter from multiple sites, and also quantitative wood anatomical data as well from several sites. But also I'll give some examples using data or samples that originally were used in a study that Jesper and co-authors, other colleagues were involved in from you know, using samples from a specific site in Finland that was quite extensively analyzed in using different parameters and analyzed in different labs around the world. So there's a good sort of benchmark and a lot of data that we have that we can compare with as well. So just looking at the raw data, so at the top left here, we have these sort of samples of Pinus sylvestris from Finland, and some like 10 series in this case. So we can compare the blue intensity against the surface intensity, and we see that actually the measurement values or the average measurements are quite similar. There's a bit of a trend difference between blue and surface intensity, and also as surface intensity has a bit of a higher variance than blue intensity data. Correlation is quite high between the two chronologies, and what we see actually at the bottom is the inter-series correlation, R bar. When we look at the blue intensity compared to surface intensity, the surface intensity generally tends to have higher inter-series correlation than the blue intensity data. And as a result, we also have sort of stronger EPS, expressed population signal statistics as well. Now, this particular site, actually, the R bar is very strong when it comes to blue intensity, and really probably one of the strongest that I've ever seen. So just to take another example, this is from Norway Spruce site in Romania. Similar story to what we have on the left side. But if you look at the bottom here, you see that actually the blue intensity data are considerably weaker in terms of the inter-series correlation. The surface intensity is much stronger in this case. There's a bit of an offset here between the blue intensity and surface intensity raw values, and that probably just has to do, I think, with one version, the blue intensity data or the samples did not contain chalk in this case, but they were just sanded, I think. So that might be the reason for the offset. Still sort of looking at the samples from Finland, if we compare the surface intensity and blue intensity data against the sort of optimal climatic season, May to August mean temperatures, and in this case, we we have 10 series of surface intensity samples, and a large number of blue intensity series to make up the chronology. So what we see is, this is how well this blue intensity sort of represents what's happening. Surface intensity, the chronology is maybe a bit closer when it comes to the sort of temperature representation. And correlation for blue is 0.65. For surface intensity, it's 0.73. So we've actually improved this over time. But you see consistently the correlation is much higher for surface intensity over that full period that we're looking at here. So here is another example of Pinus sembra from Ukraine. We have 10 samples, 10 series, but in this time the samples are aligned in relation to the heartwood-sapwood transition, which has a very notable color transition. So what happens then is that we see there's this big dip or sort of a big step in the blue intensity values from the heartwood to the sapwood. For the late wood blue intensity data, the early wood blue intensity data have a sort of corresponding sort of step as well. We just have an increase. So that's just related to the inversion of the late wood blue that we it's step that we perform. So that's why it's different. One's negative, one's positive. The delta blue intensity chronology looks like this. So this is the Jesper's sort of statistical correction of the blue intensity data, which sort of does the job pretty well, I would say. We're a little bit off the sort of similar mean values before and after the heartwood and sapwood transition. The surface intensity data, without any sort of statistical processing or basically just the raw data, just making a chronology out of that, this is what that looks like. So we see very similar sort of mean level values before and after the hardwood-sapwood transition. So that's a good sign. It indicates that this color sort of change does not affect the surface intensity data. So now I just kind of wanted to give an overview or look at a specific issue when it comes to measuring surface intensity. And with blue intensity, normally we, if we're interested in Lakewood blue intensity, we're interested in the highest density, which tends to occur in the darkest part. We're essentially trying to measure the darkest part of the ring or darkest part of the Lakewood. So it might be 15% or something percent of the darkest pixels in the Lakewood. That would be our blue intensity value. So I'll just wanted to sort of point out this one parameter in, if we use, for example, Q recorder to measure the blue intensity value, then the software is set up to essentially use the color or brightness, light intensity values to find the darkest part of the ring. So that works very well. The only problem is if we then take this concept or principle and try to measure surface intensity, we actually don't have any way of finding the darkest equivalent or the densest part of the ring using these sort of binary black-white images. So then there's a question, okay, if we're using the window-based system in Q recorder, how do we best capture surface intensity values? So we could, for example, use a fixed width, radial width value, for example, 200 pixels. Every ring has the same radial width, or the window that we're using to measure. Or we could have a sort of relative width of the window. So in relation to the full size of a particular ring, it might be, for example, 20% of the ring radial width, and I guess we would ideally like to have the smallest possible window in this sense, so that we're able to capture sort of this area of highest density. So just keep that in mind as we move forward. So here's an example actually of, let's try to quickly explain this, using different window settings to basically, and then looking at the inner series correlation of those series. So what we have here on the left side is an absolute width, so 50 pixels, 100, 200, 300 pixels. So that's a bit rigid. And then we have 40%, 30%, all the way down to 5% of the radial width. And so ideally, we would want to have our signal is here, somewhere here where we have the sort of smallest window, a radial width window size. Or here sort of looking at the relative size, then maybe like 10% or 5%. That should be the part of the ring where we have the highest density. The only issue is that, I mean, we can look at how this changes if we have 3, 6, or 9 series, but in general, we see that the highest inner series correlation is somewhere around 20% of the width of the window, or of the ring rather. So that's maybe not as small as we would like in order to get the strongest climatic signal, but right now that's where we get our strongest inner series correlation, the common signal between these series. So we could just look at what the express population signal looks at. So even with just 6 or 9 series, for most of these settings, we can get an EPS above 0.85. That drops off at the very sort of smallest window sizes. So it's much more, obviously, then we would need more samples to get a representative chronology. So we can express the EPS in relation to the number of series that we have. So, and here's just sort of 3 common settings, or 80. So 80 in this case is 20% relative width, 90 is 10, 95 is 5%. So we see, again, just with a few series, we can get up to 0.85, but really with, it's this area around here where we have 80%, or 20% of the radial width, where we have the strongest signal and we need the fewest series to get a representative chronology. The interesting thing is then that if we look at the correlation with the temperature, sort of the climate signal, based on these series, what we see actually, even though our strongest inner series correlation is at 20%, actually the climate signal, we get the strongest climate signal when we use 15 or 10%. So that makes sense. We're getting closer and closer to the point of highest density. But actually, in theory, there's no reason why the inner series correlation or even the climate signal should not be, we would expect that it would still be quite strong, even going to 10% or even 5%. So this kind of points to a limitation potentially of the way that we are measuring, representing the parameter and the measurements, and likely this relates to an introduction of noise, which limits the signal that we can get out of the data at when we have very small sort of radial width settings. So if we kind of look at this different sort of the temperature, the climate correlation of different parameters based that Jesper looked at in his study, with sort of the response of blue intensity to temperature, and then also here the density, sort of X-ray density chronologies, and then anatomical sort of quantitative wood anatomical data sets. We see sort of this spread in correlation going from lower to higher when we look at the lower resolution and the higher resolution systems and techniques. So with surface intensity right now, we're somewhere around 0.71, 0.72, which kind of we end up somewhere here around this area. So I just wanted to point out that actually right now we don't have any optimal way of measuring surface intensity. And there are certain limitations of the software if we use, for example, QRecorder or actually any other software that could measure surface intensity in some way. Specifically, if we talk about QRecorder, right now there's a bit of a hard limit of 500 pixels. So with very high resolution images, that limits the sort of the size of the window that we can use. So that if we could use a larger window, that would probably reduce the amount of noise. And we're also not really able to automatically or semi-automatically measure the ring boundaries. So the measurement of sort of placing each individual point is quite tedious. And we also have to be very careful with the orientation of the boxes of, sort of the area that is used to calculate the surface intensity value. So actually having something like a more flexible boundary sort of system to represent the boundary of one ring and the next would be very useful, because then it would make it easier to for sort of the late width surface intensity to get that area of highest density and not, for example, include the early wood of the next ring, which then obviously introduces some noise. And then, if we wanted to measure intra-annually, sort of some specific sections of the ring, not necessarily just the very end. Right now, also, we don't really have a good way of having sort of like a relative radial width measurement that we could sort of move up and down to different sort of bands and segments within the ring. So that would be very helpful as well. And also right now, actually, we had a bit of an issue that having a black and white image, it's also a little bit difficult to see the points and the placements. And so that's just kind of a more sort of minor issue, but it can also make it a little bit more difficult to measure these. But potentially, if we were able to, right now, we're not utilizing the full potential of these high resolution images. And it would be nice, but potentially, actually, if we could do this in a more effective way, I would expect that the sort of the strength, the sort of inner series correlations, and then also the climate signal would probably improve even further, and we would probably be on the same playing field as quantitative wood anatomical data sets. So there's still some work to do in this sense. So I just wanted to look at some experiments that we did with staining, both in relation to blue intensity and surface intensity. And as I mentioned, sort of this was like, for us, this was an early way to try to improve the contrast of the images, so to differentiate from the cell wall area, the cell wall and the lumina. And we just wanted to see, okay, by staining the sample, does this affect potentially in any way the data that we're producing? So looking at surface intensity data, sort of a stained and unstained subset, so the same samples, just different parts of the sample, so one part stained, one part unstained. And what we see when we sort of average the series together and look at the raw measurement values, we have a very similar, very similar chronologies, but there is a bit of an offset. So this sort of indicates that by staining the sample, we changed the relationship between the cell wall, sort of the thickness of the cell wall, and the lumina. But it seems that actually we do this this happens in a way that's quite consistent throughout the whole sample or between samples. So if we look at z-scores or look at a sort of index after standardizing, we see that the two chronologies are very similar. And the correlation in this case for the stained and unstained or non-stained 0.941. So essentially that's, that could just be measurement error essentially. And the correlation of the non-stained version with temperature is 0.731, and the stained version is 0.707. So actually, with the staining, we do reduce a little bit, at least the sort of the climate signal when it comes to surface intensity. We kind of weaken that. We're probably introducing some amount of noise, which then reduces the correlation. But one take-home message from this is that we could use stained and non-stained chronologies or sort of developed chronologies, but probably it would not be a good idea to mix them if we need absolute values or differences in absolute values. For example, if we're using RCS detrending to develop a reconstruction, that could cause problems. But if we only need, or if we're interested in the relative values and we detrend the data in a certain way that we don't preserve these absolute differences, then probably it doesn't really make any difference, and we could use both versions. Looking at the blue intensity data, so this is basically the same samples, but captured with a standard scanner in the normal way. So again, we have this offset of the stained and unstained. That makes sense. It's the same as what we saw in the surface intensity data again, then sort of after standardizing, we see actually that we have the very similar chronology. So the correlation between the two series, 0.927, so essentially identical or more or less. Interestingly, in this case, what we see is that the unstained version, the correlation is 0.61 with temperature. And the stained version, in this case, actually, the correlation jumps up noticeably to 0.65. So in this case, by sort of applying or staining the sample in a consistent way, we actually end up with a chronology which has a higher climate response, temperature response. And this potentially could point to maybe, by doing this or staining the sample in this way, that we might be in this way able to remove maybe some color discoloration, localized discoloration, and then end up with a series that's more consistent or with a higher inter-series correlation between series. And potentially this might be a way of, even with, say, hardwood-sapwood transitions and color differences that are more pronounced, if we could stain the sample in a sort of uniform way, we could, this might actually be a way of bypassing some of the color biases, even when using normal scanner systems. So just wanted to mention that. It's quite exciting, I think. We kind of wanted to find out a little bit more about how well surface intensity performs, or how sort of well obtaining an image from the surface of a sample, how that compares to a standard anatomical thin section slide. So what we did was actually compare a binary blue surface intensity, or sort of binary surface image, sort of reflected light image, with an anatomical transmitted light image, which is used for quantitative wood anatomy, for example, measurements. And then we took that and actually converted to a binary format. So we have two binary versions of a transmitted and a reflected light sort of image, or of the same sample. Now, if we look at several series and compare the surface imaging from sort of the surface, sort of the reflected light version with the transmitted light version, we see something similar to what we were looking at just before, that the surface intensity values that we get from these two sets of images are very, very similar. But there is an offset. So actually, this might be related to the way we're performing the imaging, and how maybe the lighting of the sample, the details that we're capturing, and potentially even this might extend to using different systems to capture the images. But essentially, again, if we don't care about absolute differences, then we're essentially ending up with the same chronology, or the same data. So in this sense, the surface intensity from the surface of the sample using reflected light more or less gives us very similar, or essentially the same information as what we would be able to get from a anatomical slide. So that's, I think, quite encouraging. Correlation 0.91. Again, we did not measure exactly in the same places, so that might account for some of that difference. But interestingly, if we look at the R bar for different radial width measurements or windows, these are very similar, except when we get to the very small windows. And what we see actually with surface intensity from the reflected light of the surface of the sample, this drops off quite a lot when we have very narrow windows. But actually for the anatomical slides, this actually stays relatively high. So we have higher R bar at even when we have these very narrow windows. And this just suggests, I think, that for the reflected light version, we just have more noise for whatever reason. I have some ideas about why that is, but quite interesting, I think, to compare this in such a way. So now, basically moving a little bit beyond surface intensity, and this is, I think, potentially quite exciting stuff, is this idea of actually taking these high-resolution surface images of the surface from reflected light imaging and doing anatomical or quantitative wood anatomical style analyses, and trying to generate similar data. And what we have here, we sort of started experimenting with this and tried to generate a few series or chronologies based on this. And so here's actually an example of using this surface reflected light image in Roxas as we would with anatomical thin section slides or thin section images. And just to kind of show you how well, or the software handles, or how well the images perform, I guess. And what we have is actually, I think this actually looks pretty good. Maybe there are still some improvements that could be made. But what we do see, if we kind of zoom in a little bit, so boundary of the rings right here, sometimes we have some cells which are conjoined, and so we're not really able to have accurate measurements of the sort of the cell dimensions. So those have to be excluded. But fortunately, in most cases with really good quality, high quality images that have a good sort of surface, good surfacing, we don't really see so much of that happening. Or definitely not in the late wood, maybe in the early wood. This happens a little bit more because we have thinner cell walls in that part of the ring. So you can see that here, example of cells that don't quite work so well. But actually, for the most part, we were quite pleasantly surprised that actually this works fairly well. So another sort of moving beyond conifers, we started experimenting with some. This is a species, Cedrela odorata. So basically, we wanted to see, if we look at a standard scan or from a regular scanner system, high resolution image of this, anatomically much more complex and structurally more complicated sample, what sort of details can we see? And actually, what would it look like if we use a high resolution image and try to convert it to a binary format? And so you see that here in the middle and on the right side, that actually it looks pretty good in terms of the structures that we can represent and capture. And I think then it would be quite interesting, both in terms of, using some software such as Roxas or some other software to measure certain structures based on maybe the dimensions or certain properties. But potentially, rather than just relying on the binary, maybe we could actually have a look at the full color image and then even have some look at, for example, some brightness properties, or look at sort of the reflected, the light intensity characteristics, and maybe use that as well in some way to analyze individual structures or subsample or subset the structures that we can analyze. But so this was kind of an early test of this approach on sort of hardwood samples or moving away from conifers. And so this is something that we started to experiment with quite recently with colleagues or collaborators from South America, specifically Francisco Zuluaga from the Nueva Granada Military University in Colombia, and also with Mario Tomasiolo Filo and from the University of Sao Paulo and his group. So we started looking at Cedrela odorata and also some Araucaria from Brazil. And actually now we would also like to process some Araucaria samples with the help of Ignacio Mundo and also Rob Wilson, who's been working with those samples. So Ignacio from the Dendrochronological Lab in Mendoza in Argentina. So I think it would be really cool then to take these sort of methods and try to apply it in a completely different setting with different species, different in climatic environment as well. So we're sort of in very early stages of that. Okay, so I'll just try to finish off here. So this was kind of a quick overview of the surface intensity or high resolution sort of techniques using binary segmentation of images to develop a blue intensity like parameter by utilizing and looking at the anatomical structure of the wood. So in this way, we're able to sort of develop a colorless blue intensity-like parameter from high-resolution images without any influence of light intensity and differences in light intensity. So hopefully this parameter will allow us to resolve some of these light intensity or color bias issues that we experience with blue intensity. And hopefully it will also allow us to resolve some of these resolution-related issues where simply, scanner-based images don't quite cut it anymore. Of course, this opens up the door to looking at and extracting intra-annual information from the samples. or from these images, and then to kind of use that to develop quantitative wood anatomical like data sets using the reflected light sort of images from the sample surface. So, you know, there are some caveats, of course. It's not as cheap or fast as regular blue intensity, but I think in some circumstances that might be the better direction to go, especially if there are substantial issues with the blue intensity data that we can't really resolve in any other way. And it is still, all of this is still quite new, pretty experimental. So we need to do a lot more additional testing to understand these parameters, the behavior, their behavior, and how best to work with this particular parameter in a different set of wide range of different contexts. So there's that. Of course, there's a possibility that we are creating some new biases that we are either not aware of, or something having to do with, for example, the image processing, the manipulation of the images, and the way we are measuring it, of course, as well. So that's something to think about. And you know, we had a few discussions about, okay, the images are awesome and we can do a lot with it, but at the moment it does take quite a lot of time. Other systems maybe could generate similar type of data, or sort of images with similar resolution or lower resolution, but sufficient for surface intensity measurements. So if we look at, for example, Atrix or Dendral Elevator that the Dan Griffin's been involved in developing, or Skippy, sort of looking at the WSL and sort of these camera-based systems, that might be one way forward to kind of find a balance between data quality and the amount of time and effort that we need to put in. So very quick sort of sum up. So some advantages potentially is the high resolution of the surface intensity parameter. We don't have color biases, or we can get around color biases. Typically, SI has a stronger common signal than blue intensity. The climate signal is typically also stronger and usually better than blue intensity, although not in all cases. And potentially it could be as good as some quantitative wood anatomical sort of parameter data sets. I think there's still some experimentation to do to figure out whether or not SI is currently able to give us better representation of climate extremes, for example. So very small rings, and how well we can represent sort of small growth rings. We can maybe also use it to develop an early wood surface intensity version of sort of this parameter, which would also not be biased by sort of color and light intensity differences or changes. So this a lot of this stuff is explored in a paper that still putting together and sort of in the final stages of preparing right now. So hopefully this will be done relatively soon. And just to mention some work that's ongoing, we're trying to look at some ways of making this cheaper and faster. I had some, you know, discussions, or we had some email exchanges with Lars Åke Larsson. Potentially there, I don't know if there would be some ways of making updates to QRecorder to try to make it possible to work with these high resolution images more effectively. Or, you know, with Georg von Arx and Roxas, that would be another potential avenue. And that I had actually talked in quite a lot of detail with Dan Griffin about maybe also implementing something in the Dendral Elevator system that he's been working with and developing. So looking at intra-annual information, I think that's another cool potential avenue and step that we could look at. Or that we're looking at right now. And then, of course, to go beyond Europe and the temperate climates, and look at maybe tropical species or hardwoods and different environments as well. I think that's one direction that we're trying to go now as well. And ultimately, it would be really nice, I think, to do a QWA, quantitative wood anatomical comparison with the surface reflected light version a similar data set, looking at how well we can represent the anatomical structure and how the data sets compare of the sort of regular wood anatomical sort of traditional approach versus something from the reflected light version of the images. And we're also using both the surface intensity and now also surface quantitative wood anatomical parameters as part of developing temperature reconstructions within the replicate network. So that's ongoing. So thank you very much. That's everything. Hopefully I didn't take up too much time.
Brilliant, Milos. Thanks very much. Virtual claps from everyone, I guess, or some people. Any questions, everyone? I'm not going to rush away to get my car this time, so I can moderate it better this week. So if people could put their hands up through MS Teams, and then I can call your names out. I think that's probably the easiest. I have lots of questions, but I'll wait. I'll hold. Any questions, anyone? Then I will start. A relatively simple one. You were talking about the window size as a limitation because your images are so large at 72,000 dpi. Yeah. Have you just tried to see what would happen if you just degraded the image down to 50%, so around the 35,000, to see that by expanding the relative window size, then did that improve the results?
I think we haven't actually done that. That I think is sort of one of the next steps that we want to explore, kind of where the sweet spot is in terms of balancing resolution, having a very, very high resolution image compared to the quality of the data that we're getting out of it. And that would be one thing. I think if we lower the resolution by half, I think for surface intensity we could still get a just as good a value or a measurement as we do right now with even higher resolution. But I think for something like QWA style analyses, we might actually need the high resolution.
Fair enough. Speaking of which, Georg is the next.
Yeah, thank you, Milos. Great presentation. I hope you can hear me. I have two questions. One is a small one. I think in one of your results you showed that taking a window of 20% towards the end of the ring shows the strongest, was it common signal, I guess? Now, my first question there was, is this roughly corresponding to the late wood? Maybe you can comment on this, so that's an easy one. And then, if I'm not mistaken, well, you showed, of course, that discoloration is an issue and that by your painting and applying the chalk, you can homogenize this. Still, if I remember correctly, in one of your data sets, you showed that surprisingly or not, it didn't perform better than without staining. And my question then there would be, well, where would the noise come from? Now I don't know whether we lost Milos.
He did freeze. Milos,
he froze, right?
Yeah, he did freeze.
Is he still around?
Yeah. He's not in the list, and he's going to have to log back in.
Okay, well, let's wait and see, and if so, I can repeat whatever is required. But let's.
He's back again. You're going to have to repeat, I think.
Okay, I guess you didn't hear anything, Milos, right?
Milos, your microphone's
you are muted, Milos. Yeah. Milos, you are still muted.
Yes. Okay. No, I did not. Yeah.
I did not hear anything. So then I restart. So a great presentation.
Sorry for
Thank
that.
you very much.
Thank you.
I have two questions. The first one is very simple. In one of your early analyses that you showed today, you showed that for the 20% last parts of the ring, you got the strongest common signal.
Yes.
And my question there was, does this roughly correspond to the late wood in your material? And the second question, if I may append this already, you also showed us the advantages of using the staining and applying chalk to homogenize contrast, especially with wood samples that show discoloration issues. Still, in one of your data sets, it seems that this treatment didn't improve. On the contrary, And you then mentioned something about the noise, and I was just wondering what sort of noise do you think about when you apply this contrast homogenization or surface treatment?
Mm-hmm. Right. So, so to go back to, sorry, what was the first question?
Sorry, I took too long for the
No,
second.
no, it's
It
okay.
was about 20% how it
Oh yeah,
corresponds
okay,
to
if it corresponds. So I actually I didn't specifically look at that, but I imagine it might more or less correspond to that, or it might be kind of close to the part of the ring that might be, you know, where we see the late wood. But I did not specifically check actually, so I can't definitively answer that. I'll take the lot. The staining. That was the next question, correct? So yeah, I think what's really interesting is that the staining doesn't really help us when we're with the surface intensity parameter, where we have sort of the binary black-white high resolution representation of the sort of structure, and just with, I mean, I guess I could imagine that if you know, there might be little small deviations maybe in the way that the staining is applied, even after all the steps that we take to try to make sure that there are no, you know, it's kind of as close to the original version of sort of unstained version of the sample. But I can imagine that even just that process would introduce some noise, in the sense that it might maybe change the properties, or like the relative proportion of the size of certain anatomical structures. Maybe that would be one reason why then we don't get really any benefit, at least with the high resolution images. But the degradation is not really so dramatic. It's maybe, okay, it's a little bit weaker, but not so much. But for SI, for surface intensity or using these high resolution images, essentially there's no reason for us to apply staining, especially with the light filter that we're using, the polarization filter. We can get sufficient contrast to basically not have to worry about staining. Interestingly, when looking at this blue intensity version of the data, that's actually where we do see an improvement by applying the stain and then sort of doing a measurement of the stained version. And that's, you know, we had a few discussions and talks about this, and I like to think that this indicates that by staining the sample and then measuring it, we're able to maybe remove some of these little discoloration blemishes or changes in the color version of the scan, or sort of the regular scan that we have, that we then use to measure blue intensity. So you know, we haven't tested this in detail. For example, taking a sample with a very pronounced hardwood sapwood color difference and then staining the whole sample, reprocessing it, and then scanning it and measuring it. So we've only done this with these samples, these finished samples, where really these differences are minimal. But even so, we get some improvement. And that's maybe encouraging. I don't know. I think we need to explore this maybe in more detail. But it would be interesting to see what sort of a stained version of a blue intensity chronology would look like in a sample that has severe discoloration issues. I think that would be sort of the next thing that would be great to test. And, you know, it would be great then if this would be one approach, potential approach to minimize or remove color biases, even when using a regular scanner. I think that would be great for everyone, for the whole blue community. So
just briefly, for my understanding, Milos,
yes.
and then Rob, I will not ask more questions. But the reason why for surface intensity it doesn't matter so much is because anyways you then move to a binary image.
Yes.
And so the chalk gives already enough good white contrast, let's say, so that you don't care about any color of the walls.
Yeah.
And this is why it doesn't matter there, right? Whereas in the blue intensity, where you saw improvements with the classical methods, there, of course, we work at low resolution, and it does matter that you get rid of the discoloration issues.
Yeah, I think exactly. It just points to, with the binary images, we're relying just on the sort of anatomical structure and the relative dimensions of the structure of the wood, rather than actually any color or sort of light intensity differences, which is what we get with the scanner system. So that, I think, could be the reason why we don't see an improvement with the high resolution binary, and we do see an improvement with the scanner-based sort of stained and unstained version. Yeah. I think, was there another question I missed? Sorry.
Yeah,
it's been a long day.
well, I'm gonna drop my hand and give it over to Jesper. So Jesper, you're up.
Okay, so I want to piggyback on what Rob asked earlier about reducing the file size or the image size, because this is actually a way for you to increase the frame width. If you reduce the file size, you increase the frame width by double. And that should, in theory, give you more representativity of the ring, and maybe even a higher R-bar or temperature signal or something like this. And then you can play games sort of where the convergence zone is for the climate signal. I mean, that's just a theoretical example, but for me, you have way too few cells analyzed in co-recorder. In the wood anatomy, we use maybe 50 or even 100 cells in the tangential direction, and you are looking at 10 or something. And I think that's why you have this dramatic decrease in R-bar when you go to smaller percentages. How can you comment on that?
Yeah, no, I think you're totally right. So, I mean, there's two ways of approaching it, right? Either we can reduce image resolution or the file size. The file size itself is actually not really a limitation in terms of data, because the binary images, even though we have a lot of pixels, it's just black and white pixels. So the file sizes actually are quite, small, tens of megabytes in this case. But yeah, in terms of the sort of resolution, having a sort of smaller, more image would allow us then, even with the limitations of the software in its current form, to have measure a large area. I mean, another way of doing it would be to measure multiple radii, right, or in multiple positions, and then averaging that together. That would be without losing any resolution. It would be another approach. But I think really, yes, we can kind of play these games, but right now there's still some kind of trade-off that we have to make. And ultimately, I think what it comes down to is, developing the measurement systems to allow us to measure in a way that minimizes or sort of gives us the best possible data, and sort of minimizes any of these, introduction of noise by having a small window to work with, to play with. And so, I mean, right now, the only consequence for us is that we just need to measure. If we stick to that same resolution, we just need to measure a few extra samples to get adequate, inter series correlation. And then what we see is that even with this limitation, and even though we're getting a relatively small representation of the ring, or the particular part of the ring that we're interested in, we're still getting, we're still outperforming blue intensity, right? Where there we have quite large parts of the ring that we're using to produce the blue intensity value and measurement. So it's still working, surprisingly, it's still working pretty well, even though, okay, we might need more samples, but in terms of climate signal, it's still there. Maybe it could probably still be improved further, and maybe we would get away with having an even narrower window and a smaller window and an even higher correlation with the temperature. But yeah, I think then for that we would need something like kind of flexible system, which would allow us to delineate and measure exactly where the ring boundary is, and then have a kind of like this small kind of slice along the end part of the late wood to basically give us the best possible signal. So I think we'll get there. It's still very much usable, and we still have very high quality data, but of course it could be improved further. And yeah.
So a hybrid between Roxas and co-recorder would be.
Yes. Well, this is where, I mentioned that actually at Ameridendro in the summer, I talked quite extensively. We had a chat with Dan Griffin, and he was quite excited about, all this stuff. And he thought that it actually might be possible to integrate a lot of the sort of all the processes and the that we need to do these kinds of measurements within the Dendro elevator sort of system and software. Okay, it might take some time, but I think that might be one direction that we could, where we could go, because the system, from what I've seen, I don't know it that well, or I've only seen some examples of how it works, but certainly there's the flexibility, I think, to make additions and changes to use high resolution images. It's already set up to do that, and now it would just be essentially adding some additional functionality to get these measurements that we're interested in doing. So that might be one direction we could go. So.
Maybe it's a sort of cautionary thing. I mean, because we've done so much measurement now on multiple sites, not just single sites. So I think a lot of these tests are always on single sites, and okay, this is the R bar, and we go up a few more series and so forth. But I think it doesn't, whether you're talking about traditional blue or now the high resolution systems are coming on, and plus what you're talking about, I think maybe groups need to consider multiple sites as well, because if you've got one site, it behaves so forth, but when you're averaging maybe 3 sites, then I think all of these variables, all of these parameters must converge to a certain degree, because when we're talking about noise, the noise is systematically random, unless there's a resolution bias. That's a different story. But if the noise is, especially if you go high resolution and you're adding in some degree of noise, then that would theoretically minimize by more samples per the site, but also more sites in an area where all the assumption is, right? So and that goes to traditional blue as well. I remember with the early Yukon work, because the rings were so narrow, we did actually get quite a good calibration, but we needed more than 10 sites. At the individual site level, it was, as you say, 0.6. But you put then 10 sites together, and suddenly you're going above that kind of magical 0.7 mark, if that's kind of a minimum that we're aspiring to. So it's just worth for other people, especially those in the group, if there's anyone working with the new high resolution systems, is we're doing lots of experiments with ATRACS, and it isn't this magical, hey, we've got this beautiful signal coming out of it, because I think there is more information. So I'm not going to call it noise. There's more information in there, and so it's not a simple improve your resolution and then you're going to get this magical, sexy, improved record at the end of it. I think we've got to be quite careful jumping to these high resolutions, because, as you say, there's more there. So, but I think that's the way we're looking at it as well.
I mean, so far, based on, I think it works, or SI, surface intensity, works quite well in the majority of sites, but it doesn't always outperform blue intensity, and particularly like in areas where the blue intensity is quite well behaved and the signal is very strong, and the climate signal in the blue data, there aren't any big issues, and sometimes it performs similarly, but doesn't necessarily.
But in those situations where the blue is doing pretty well, are the rings relatively wide, or can they be quite tight ringed as well?
It can also. It definitely, usually there are fewer issues in with sites where you don't have as many sort of tight ring sections, but I think then it also comes down to if you don't have any substantial sort of color related issues, then you might not get, and you don't have a lot of very narrow rings, then you might not get that much additional improvement. But another thing is, one thing is in terms of the climate signal, looking at maybe intermediate sort of decadal trends and interannual variability, but then if we start looking at long chronologies and including subfossil wood and discolored wood, and then I think that's where this kind of approach can really, I think, be really kind of make sure that we're not including those biases in any reconstruction. So it's the further back in time we go, and also then, you know, if we have lower replication and we have all these kind of issues that come up, I think this is a system that, or sort of this is an approach or a parameter that could really help out in those early portions of chronologies and further back in time. Yeah.
I mean, and this is maybe a question to you and Jesper and anyone else, maybe Georg, is when you have really quite ancient subfossil material, so we're more than a few thousand years old, and you know it's always lighter, right? Clearly the lignin is broken down and all this. If you did wood anatomy on such material, does the cell wall structure, is that still retained, or is that biased? Because that's what we're talking about here. Is there still a bias in that lighter material?
It's a good question. I think that's one for you. Yeah, Jesper or Georg, probably.
He's smiling. He's smiling because he has the answer. You can tell by the smile.
I don't have the answer, but I'm currently working with a very long quantitative anatomical series from Yamal, and that's a sort of river bed material. And when you go further back in time, you can see that the cell walls are ruptured. So and the wood is sometimes lighter in your hand. You could feel the difference between a modern sample and a subfossil sample. So something has left sort of the wood, and then it remains to be seen if that has an effect on the wood anatomy. It for sure will have an effect on the X-ray densitometry. So Stefan Klesse and I and Patrick Fonti, we have a small experiment going on now where we will do wood anatomy on an ancient part of the Yamal, and also X-ray densitometry, and then compare with a modern section for X-ray densitometry and wood anatomy. So it remains to be seen, but I would suspect that there will be at least a big difference between the modern and the ancient for the X-ray, and maybe even for the wood anatomy. I mean, I would think so, because the samples, they look like they've been through a lot. So, but I can just sort of tease you with that. I cannot say more.
Maybe I want to just add something. So I agree, of course, to all you said, Jesper. The nice thing here is that you can see what you measure, right? And usually when you have a thin section that is highly degraded, you see that and you exclude those rings. It's probably, there is a gray zone where you're unsure, exclude, include, and exactly there it is important to perform such experiments that Jesper just mentioned. My perception there is a bit like osteoporosis, right? You probably all know that lignin is kind of a substance that is in this mesh of cellulose interweaved, and basically, well, the dimensions might stay the same for quite a bit of degradation, but then, of course, from a certain point on, you also start to see in the anatomical section this shrinkage of the dimensions. Well, that's just all I wanted to add.
Yeah, interesting.
Any other questions? Well, actually, I have one quick question, because you keep talking about staining, but actually never said anything about what the staining process is.
Right.
And I've got two. In your original iteration, when you started talking about surface intensity, you were blackening the samples.
Yeah.
And it seems to be you're not doing that now.
We don't need to. No.
Right. Yeah. So what is when you stain, what staining are you doing? And I presumably there are many ways of staining. So if you've got a species that has a very, very distinct heartwood sapwood color change, you need to stain it more if you're kind of thinking that staining might help. So what are the stain? I have no experience.
Yeah, we're basically just using a ethanol based marker, like black marker. And
you're just
it's literally I mean, then what we actually have to do is then do kind of like a final cut, because if we just do that and leave it, it tends to fill in everything. So what we need to do is kind of let that dry, then get the surface of the sample like a little bit moist, and then after that make basically like a few more cuts. Usually the marker penetrates quite deep down, so even if we need to make more than one cut or multiple cuts, we can do that without really, losing the stain or the staining of the. So that, I mean, that works quite well, and it's just kind of been through trial and error, figuring out the best way to get that and get a result that's sort of consistent and you don't have any weird things going on. But it's pretty straightforward. Yeah, it's not something that's super involved and difficult to do. Yeah.
Anyone else? Any questions from the floor? If not, I'd like to thank Milos for a great talk.
Thank you so much.
And at the moment, we have nothing else on the calendar for iBind, so I'll probably send an email around because there's lots of papers being published all over the place now. So there's plenty of groups using Blue for a variety of different projects now. So we might have to just headhunt people to give a talk just for the sake that they've got a new paper out. But we can look into that. So, well, thank you very much, Milos. Virtual claps from everyone. I think that's possible. Well, I'll see everyone, and we'll keep everyone posted with regards to the Blue Intensity special issue. Probably an email coming out in the next few weeks. And if anyone has a talk they want to offer, just email me or anyone on the committee, and we can set it up relatively easily. Okie doke.
Cool.
Brilliant. Thanks very much, everyone. See ya. Ta-da. Thanks.